Hi, my name is Andrew Knight. Today I'm going to talk about Schrödinger's cat, Wigner's friend, and ultimately whether or not it's actually possible to create macroscopic quantum superpositions. So I'm going to start with just an explanation essentially of what is Schrödinger's cat. Of course, I've taken this image from Wikimedia, and it's the classic image of some sort of quantum event right here that gets amplified into some interesting macroscopic state of either a living or a dead cat. Now, where did the thought experiment come from? Well, it came from Erwin Schrödinger himself to point out how absurd it was to assume that quantum mechanics universally applied to everything as opposed to just small or microscopic systems. However, the thought experiment has been taken very seriously, especially in the past decade or two, by scholars in physics and philosophy of physics who have used the in-principle possibility of Schrödinger's cat or Wigner's friend to then show further conclusions and results and no-go theorems. So I want to address this today. So first of all, what do I mean by Schrödinger's cat? Really what I mean is, first of all, a quantum superposition. What is that? A superposition of distinct eigenstates of some observable, such as a measurement operator. Now, I'm going to be talking specifically about superpositions in the position basis without loss of generality, but specifically that is what we're most used to because in the real world we measure things by their position, and also it's what makes arguably the Schrödinger's cat and Wigner's friend thought experiments so odd is because we can in fact in this example see a living cat corresponding to a position of a living cat, and we can see a dead cat, again, corresponding to position. So that's why I'm going to look specifically at position basis. So a quantum superposition, that is macroscopic. And what I mean by that is, at the very least, something that you could see. Even the smallest visible speck of dust would certainly count as something macroscopic. I'm not including things like, they call them mesoscopic objects, and I think they're just using that word because it sounds bigger than microscopic, but really you can't even see a buckyball with an optical microscope, so I'm not sure how that's not microscopic. But in any event, I'm not including that. I'm not including things like macroscopic effects like superconductivity or superfluidity. I'm talking about a macroscopic quantum superposition such as a speck of dust in distinct position eigenstates. And then finally, a macroscopic quantum superposition that can be measured by some interference experiment that is possible in principle. Now, before I go any further, I need to point out, as so few papers and references do, that you can never confirm a superposition or interference effects with a single trial or two trials or even 10 or probably 100 or 1,000 trials. I mean, maybe 1,000 trials. The point is you need lots of them and able to then infer an interference effect or a superposition state. So already it's problematic because even if you could produce a Schrödinger's cat, a single measurement of that system in any basis would never yield conclusive evidence that it was in a superposition state. But let's just assume, again, for the sake of argument, that, yeah, we can do this a million times. We can create a million Schrödinger's cats so that we can, in fact, test whether or not it was in a superposition state. And then, of course, I'm including Wigner's friend, which is the conscious counterpart to Schrödinger's cat. Having said that, if a conscious computer could be created from a quantum computer, then that might be a different question, because a quantum computer itself may not be macroscopic in the way that I'm referring to. I don't know yet. I haven't done that analysis. But whether or not a computer of any kind, including a quantum computer, could be conscious, I've already addressed that in a couple of papers as well as a couple of videos on YouTube, and argue that consciousness cannot be algorithmic and therefore it cannot be created by a computer. But nevertheless, with those caveats, let me move on. My goal is to show in this video that this is simply impossible. It's simply impossible to create a Schrödinger's cat or Wigner's friend, or ultimately to measure a macroscopic quantum superposition. So let me start at the basics. How do you create a superposition in the first place? Well, let's rely on Heisenberg and just good old-fashioned quantum uncertainty in order to allow a quantum wave packet to disperse over time. So this is basically the Heisenberg uncertainty principle, or the uncertainty relation. And so very simply, imagine some object that's moving in a certain direction. And of course, I'm being very loose here because I'm showing you the position of it right here, but we don't necessarily know its position. I'm just saying in general, there's some object that happens to be moving, with some momentum that may be fuzzy. Now, let's localize this to within some width delta x. Now, you can do it, for example, by passing it through a slit of width x. If the object makes it through, then you've localized it in the x in that dimension to that delta x. Now, if you do that, what uncertainty tells us is that there will be some corresponding spread in the resulting momentum of that object. And that gets manifested into essentially unpredictability in where you're going to find it at a later date. So, of course, I've kind of very roughly said, well, this means now that those momenta spread turn into, this is very rough, right? I mean, if it actually was a single slit, then this momentum distribution might look like the Fraunhofer distribution with edge effects. The point is, there's going to be some spread as a result of that localization. And then, so where can that particle be found later? And of course, now I have, 5 gray spots just corresponding to the fact that maybe it could be found here or here or here or lots of different places. But what's interesting about this, of course, is that the spread here is larger than the dimension of the object itself. And what that would allow us to do is, like, for example, a 2-slit or a double-slit interference experiment, where now we pass it through a double slit and we've got a coherent wave that passes through it, and then now we can see the interesting interference effects of it. But you might ask, how long does it actually take for an object to spread in this way due to some localization? Well, let's compare electrons, dust particles, and a cat. Well, I'm not going to compare them all, but the point is, notice up here that the relation depends on momentum, which depends on mass. So for a very, very, very small mass like that of an electron, you can compete with the insanely small magnitude of Planck's constant, so you can actually, in a real lab, show interference effects for an electron. Now, having said that, it took a very long time to do so. It was 1926, I think, which is recent, right? Very recent in human history, in which an electron was shown to have interference effects or a wave nature. But again, that's because the mass of the electron is so small. But compare that to a dust particle. How long would it take, very roughly, back of the envelope calculation, for a dust particle to spread so that the spread is greater than its own dimension? so that you could do some sort of double slit interference experiment? Well, it's very easy to do the calculation, and you get a little over 1 million years. So, and that's just for a dust particle. For a cat, it's far, far longer than that. So it is certainly untenable and actually physically impossible to create a macroscopic quantum superposition through the process of dispersion. And I didn't explain why. And the reason is that in that, for example, in the case of the dust particle, during that 1 million years, that dust particle is being inundated by particles and objects and fields and stuff, cosmic microwave, background microwave radiation, that is bathing the universe. There are constant interactions that would quickly decohere any superposition or any dispersion spread in objects, and therefore you won't ever see, by dispersion, a macroscopic quantum superposition. A little more about decoherence. You can ask the question, well, how much can any given object disperse? Max Tegmark does some calculations, and he basically shows, okay, so on Earth, due to sunlight alone, the center of mass of a bowling ball cannot disperse more than, what is that, 1/100th of a femtometer, right? Something really, really tiny. And even in deep space, you still have cosmic background radiation that will not allow you to create a macroscopic quantum superposition. Even for a dust particle, you're still at 10 nanometers, which is smaller than the dimension of the dust particle itself. So you can't do it by dispersion. And I don't think anyone who understands quantum mechanics and Schrödinger's cat argues that you can create macroscopic superpositions via the process of dispersion. Instead, what is said is that you create the superposition by amplification, a von Neumann chain of amplification. And it goes something like this. Let's start with some container C at time t0, in which we're going to contain the Schrödinger cat experiment, or actually in this example, we're going to use Wigner's friend. Inside that container is some object O in a superposition of states A and B. I've left out normalization constants, obviously. And those states A and B correspond to semi-classical localizations at positions A or B. So you start off with this superposition of this tiny object. Also inside the container is some measuring device that's in some initial state. It has not yet measured or correlated to the object, so it's in state M0. And then you have Wigner's friend, F, who also is in some initial state, who has not, that friend is ready to read whatever the output is of this measuring device. And then you have some super observer external to the whole container, and that's going to be Wigner, W, in some initial state. And we can assume, for the sake of argument, that there is an information isolation between Wigner and the rest of the container. That's always assumed in the literature, and let's just assume, sure, you can. In reality, I think it's going to be impossible, but I'm not even going to depend on that. I'm just going to say, okay, fine, let's assume that you actually can isolate Wigner from the rest of this container. So traditionally, the way this amplification is said to proceed is as follows. The initial system starts with the superposition state and then the initial states of the measuring device, the friend, and Wigner. And then at T1, there's some correlation event between the measuring device and the object that results then in the measuring device evolving into one of two, we call them indicator or pointer states. They're macroscopic states. So this would be, this state MA would correspond to the measuring device indicating state A. So there might be some actual physical pointer on here that then points up for A, and this state MB corresponds to the measuring device with its pointer pointing down to B, something like that. So it evolves over time from that initial state to these macroscopic indicator states. Then at time 2, the friend has now observed the measuring device and has himself evolved into macroscopic indicator states corresponding to that. So this would correspond to the friend having observed the measuring device indicating state A, and vice versa for B. Now notice that at time t2, the conventional wisdom is that Wigner still is not adequately correlated to the rest of the system inside the container, so that Wigner could, with the right experiment, again, you'd have to do lots and lots, but let's set that aside. Wigner could, with the right experiment, show interference effects and thus a superposition within the system inside the container C. And then finally, if Wigner then does open up the container to measure the system, such as by opening the container and saying, hey, friend, what did you observe? And then the friend says, oh, I measured A. Well, then that would then correlate Wigner to the rest of the system, so that this means a Wigner who has chatted with the friend, who told him that he saw the measuring device indicate A, and so forth. What I'm going to do is just write this measurement chain out. This is exactly what I just had in the last slide, but it allows you to see that from time t2 to time t3 is the window in which, as we understand this amplification chain, Wigner can perform an interference experiment to show the system in superposition. Now, it's really important to mention collapse versus non-collapse theories. If you believe that collapse of the wave function occurs, well, maybe it actually happens, at somewhere here or here or here. Well, the idea is that if collapse occurs, this Wigner would deny there is any other, right? This is the only Wigner. And he says, well, in fact, the universe or this system has collapsed so that the measurement device measured the object at position A, the friend observed that, and then told me about it. So if that's the case, then this Wigner would just say, well, collapse had to have happened sometime before T3. Or if consciousness causes collapse, which I'll discuss later, then maybe it was Wigner's consciousness that actually caused the collapse. Anyway, my point is, I'm going to assume that there's no collapse here. I'm going to assume the universality of the quantum wave state, at least to this level. So a non-collapse theory would be, for example, the many worlds interpretation of quantum mechanics, which would say, well, no, there actually are two Wigners. Now, they can't really contact each other. And so this Wigner would, from this Wigner's perspective, there is an apparent collapse because this Wigner is correlated to a world in which the object was found at A, and so forth. But there isn't actually any real collapse. It's just that this aspect of the wave state is now inaccessible to this aspect. So I'm going to go ahead and just assume no collapse in this analysis. So if this amplification chain is correct, or more importantly, if it's actually complete as it's written, then in fact there is some non-zero time between T2 and T3 in which the system inside the container is in a quantum superposition, but the observer, Wigner, who is not yet entangled with it, can in principle perform an interference experiment to show that superposition. The idea of shielding or isolation, which I mentioned before, really only serves to increase that time difference. Because if decoherence means that that time difference would be a femtosecond, okay, so then that means an actual experiment can't be done in that time period. But the idea is that it's non-zero, so with adequate shielding, you could make it from a femtosecond to 1,000,000 years, and then that's plenty of time for Wigner to do the interference experiment to show the superposition. So let's just assume, again, it's possible. But again, all that would do is just expand a non-zero time interval, and I'm going to show that actually there is zero time interval in which Wigner can show an interference effect of the inside the container. Now, to show that that time interval is actually zero, I'm going to ask a question. What does this state, what does that mean? What does it mean to, what would it mean for an object O to be located at A? Relative to what? Well, we might say relative to the measuring device, in which case, really, this is maybe the nomenclature we should use. Or maybe we mean relative to Wigner, in which case we should use this. Or maybe relative to the container or other things. That alone shows that superpositions are relative. We have to specify what we mean by a quantum state or a superposition relative to what? Well, in this example, it doesn't actually matter, and here's why. As long as the distance between positions A and B is much bigger than the coherence length, the relative coherence length, between the objects in question, then it doesn't actually make any difference. And the reason is that, well, if I want to specify this relative to this, or this relative to this, but if these two are well correlated to each other, then it doesn't really matter how I specify the state. So with that in mind, what I'm going to do now is actually look at the system from before, but instead I'm going to look at it from the perspective of the object. So now, before we do that, I've been saying, well, we can look at this object from the perspective of this, or from the perspective of this, or from the whatever, because relativity matters. Well, now I'm going to look at this from the perspective of this, and this from the perspective of this. Should be completely valid. I'm going to start now with the object. Now, the object, relative to itself, is not in superposition at time 0, time t0. But it sees the container in a superposition over positions CA and CB. In other words, relative to it, container C is in a location superposition. And so is the measuring device, and so is the friend, and so is Wigner. So if we look at the system from this perspective, then at time 0, the object, of course, is not correlated to the measuring device. But from its perspective, it sees the entire system in this entangled form where this is the measuring device located at MA from the perspective of object O, and this is the friend located at location FA relative to object O, and they're all the initial states. Now at time t1 is where it gets interesting. At time t1, there's that correlation event between the object and the measuring device, just as before. But the difference is this time, now notice that we have a fully entangled state here. So, for example, the object now, so this would be, for example, the measuring device located at MA relative to object O, having observed or evolved to an indicator state that is correlated to the location of object O at position A. And then notice that at time t1, the friend still hasn't observed the measuring device, hasn't looked at it yet, and so has not evolved into any macroscopic indicator state corresponding to the location of object O at location A. But it doesn't change that the friend is actually correlated to the measuring device and ultimately to the object at location A already at time t1. And so is Wigner. Wigner also is completely correlated to the object. So note that Wigner is already correlated to the object and therefore cannot do an interference experiment to show the object in superposition. Again, it doesn't matter if we can consider collapse or non-collapse theories of quantum mechanics. Again, here we're assuming non-collapse. So it doesn't matter whether it's this Wigner observing or this Wigner. Neither one of them can do an interference experiment because each one is correlated to the object located in a particular place relative to him. Of course, at time t2, we have the evolution of the friend into his macroscopic indicator state. So, of course, at t2, we have this friend corresponds to the state of having observed the measuring device indicating A, whereas this one has observed the measuring device indicating B, and so forth. But there still isn't any change here. We still have complete entanglement between Wigner and the object and, frankly, the rest of the system, and therefore cannot do any interference experiment to show them in superposition. And finally, at t3, same thing. Finally, Wigner opens it up and talks to the friend and becomes and evolves to a macroscopic indicator state, but was already correlated to the location of the object at t1, long before he even knew what the outcome was. A concept I'd like to just throw out there, I haven't seen it in the literature, it should be pretty clear though, is this notion of transitivity of correlation. So, there's, maybe there are three subsystems. Subsystem A is actually really well correlated to subsystem B, and then that B was not yet, but then becomes well correlated to some system C. Well, that results in an instantaneous or a simultaneous correlation between system A and system C. So that to apply that, what happened was that the correlation between the observer, Wigner, and the object O happens instantaneously or simultaneously with the event that correlates the measuring device with the object at time t1. Why? Because the observer and the device were already well correlated. So Wigner and the device were already well correlated, so once one of them gets well correlated with the object, then the other one simultaneously becomes well correlated. So what this indicates is that the original von Neumann chain is incomplete, and therefore incorrect, because it leaves out past or pre-existing entanglements. When we look from the perspective of object O, it simply allows us to see those entanglements. It allows us to realize that all those macroscopic systems, the measuring device, the friend, the container, and Wigner, and frankly the rest of the universe, are already really well correlated, so that the correlation of the object with the measuring device has the effect of simultaneous correlation with everything else. Therefore, it's not just that T3 minus T2 is small, it's that T3 minus T2 is the wrong thing to look at. Rather, it's T1 minus T1, which is 0 inherently. There is no time in which the device M or the friend F or the container C is in a superposition relative to observer Wigner. Therefore, because there's no time, because the correlation of Wigner with the object is simultaneous to the correlation of the measuring device with the object, because of that, the observer simply cannot, even in principle, perform such an interference experiment to show that superposition. So I think this actually, kind of as a side note, explains Einstein's spooky action at a distance, the apparent non-local effects in quantum mechanics. I think it explains it. Imagine system A includes something big, something macroscopic, the universe, a lab, Wigner, whatever. And system B includes some very small system, let's say some biphotons, so 2 photons that are really well correlated in a particular way. So measurement of 1 photon in system B, all that does is instantiates in the larger system A the pre-existing or the past correlations in that system B. It shouldn't be surprising that measurement of the photon 2 anywhere, even in some space-like separated measurement, would perfectly correlate with that first measurement, because that correlation already existed. And of course, there's no sending of information. Nobody has ever disputed that aspect of it, so it's not truly non-local in that sense. But I do think that clarifies or makes less spooky that entanglement. Looking at the system from the perspective of the object simply helped us to see relevant entanglements. But now that we've seen that, we can go back to the observer's perspective and see something very similar. So the state of the object from the observer's perspective, of course, was originally said it was this. But really, does it, was it from the perspective of the measuring device, from the perspective of Wigner? Well, again, it doesn't matter, because the distance between locations, positions A and B, was much larger than any relative coherence length between any of those macroscopic objects. Kind of one way I can say this is that the object then is in a superposition state of object O being localized in position A and localized in position B relative to essentially anything macroscopic. Another way of saying that, I think, is that there just is no fact about whether the object is localized at A or B relative to the measuring device, Wigner, etc. Now, a correlation event that happens at T1 causes that, that state to evolve into, now let me explain this here. So in other words, what this is this is the initial state of the measuring device, but this is still an initial state of the measuring device that is correlated to the position of the object at position A. So this is still, this correlation happens even before the measuring device has evolved by the design of the experiment to the macroscopic pointer state, which would have been, say, MA sub A here and then MB sub B here. So once that correlation event at T1 happens, we can say that the object is no longer in a superposition state relative to the device M, because there is a fact about its position relative to M. Both of these measuring devices will agree, yes, the object is in a particular position. So the question then becomes, in terms of Wigner's friend and Schrödinger's cat, given this correlation event, are object O and device M then in a superposition relative to the observer, Wigner, after time T1? And the answer is no, because the fact about the position of the object relative to the measuring device by the transitivity of correlation instantly becomes a fact about the position of the object relative to the observer. And again, that's because the device and the observer are already so well correlated. And kind of briefly, the way you might think of it is that this state, after that correlation, is really, because these are equivalent right here, it really is basically equivalent to this. But this is a state that has been measured by the measuring device in which the object is in a position A relative to Wigner. So that implies a completely entangled state right here. And again, that's still at time T1. So there is no time in which Wigner can measure a superposition of the macroscopic system involving the measuring device or the friend or the container. So what are some of the implications of this? Of course, the biggest implication is that macroscopic quantum superpositions just can't be demonstrated by any interference experiment, not because it's hard, not because it is for all practical purposes, FAPP, impossible, but because it is actually, in principle, physically impossible in this universe. Another implication then is that, well, quantum mechanics then cannot be verifiably universal, which was exactly the warning that Schrödinger gave by offering the thought experiment. There's no way to verify its universality because beyond a very, very small, a very tiny quantum superposition, there's no way to then verify a larger superposition. So there's no way to know for certain whether or not quantum mechanics is universal. Kind of in the same vein, the many worlds interpretation of quantum mechanics is itself not testable or verifiable for essentially the same reason, because there is no time period in which it's possible to show any macroscopic system in quantum superposition. And then finally, an implication is that the consciousness causes collapse hypothesis is false. So the hypothesis is essentially, if we went back to the von Neumann chain, if a collapse does occur, then it's going to occur before conscious perception. And so this hypothesis just simply says, well, it is consciousness itself that induces the collapse of the quantum wave state. Well, this analysis shows that that hypothesis has to be false. And that's because I didn't assume collapse, but nevertheless, if a collapse does occur, it happens very, very early on. It happens long before an interaction with most macroscopic objects. If we think of conscious observation as being dependent upon lots of big things, eyes and ears and so forth, then any collapse of the wave state has to occur long before any of those signals ultimately are consciously perceived by us. For further information, specifically fleshing out this explanation of why macroscopic quantum superpositions can't be measured, here are a couple of papers that I have written. For information on coherence lengths, here's a reference. For more information on the relatively newly discussed concept of relativity of quantum superpositions, here are a couple of references. And then there are so many, this is just a few biggies, but there are so many papers that assume the possibility, in principle, of doing these experiments. And many of them come to these big sweeping conclusions and no-go theorems and interesting results. And if I'm right, then that assumption is wrong. So thank you for your time.